Hi, this is Cyprien from FA4 and welcome in this new tutorial in which I will talk about beam simulation. So I'll use Salome Meca and I will show you how to simulate a very simple beam. So that's not a tutorial that should take too long time because it's pretty simple. And I'll try to go right to the point and to show you the most important stuffs. So here I just opened Salome 2017. Let's start a new project. And let's start really from scratch. Let's create the geometry. So now I have this window. And let's create first the geometry of my beam. So what I'll do is simply a beam defined in x-axis of 1 meter, and then I'll just constrain it on one hand and apply a load on the other end to show you how it works and how you create this kind of thing inside Salome. So first let's create some points here, and in x direction let's enter 1000. Okay, and then let's link the 2 points with let's link the 2 points with the vertex here. So let's select the first point, the second point. Okay, and now I get a line. So that's all for the geometry basically. As you see, it's very simple. It's just one line which represents a beam. So now let's go into the mesh module. So there's nothing because I don't have any mesh. So let's just start by creating a new mesh of this line. So 1D element, wire discretization, and now I have to put an hypothesis, and I'll just use number of segments. So let's define 3 elements to start with. Apply and close, and now I have basically created the mesh, but I have to compute that. So right click, compute. Okay, and then I get my element here. And now I have to do something else. You have to think that I will have to block one end and apply a load on the other. So I will need to have those points defined as groups in order to be able to select those components later on when I apply the boundary condition and the loads. So to do that, go in mesh, create group, and here select element. Okay. I don't know why it's always resizing like that. Anyway, okay, call that left node. Left node, and now okay, should be able to. Okay, 0, I have to select node, yeah, right. So when I select node, I see the node on the screen. And now I can select the first node here, add it, and okay, now I don't see the button, so the button is really on the bottom of the screen. They should improve that. Okay, and now I'll do the same for the right node. Right node, select, add, and click on the invisible button here. Okay, and now let's also create one group for all the elements. So I can call it elements. So you will see later on why I'm doing that. So you have to keep the button of your keyboard shift pressed while you select. Okay, so I could also just select all. That would probably work also. Okay, Now, if you go in the object browser here, you see that I have group of nodes and group of elements. Everything is done. Now let's just save that. Okay, let's save it and call it beam2. Okay. Then, so I created my mesh, everything is fine, and now I'll have to go to Aster study in order to create the command file. So, what's the... let's add a stage first. Let's add a stage, and once you add a stage, you see that all the small menus here starts to be shown, so you can start to add those to your model. So the first step is to read a mesh. So you have to read your mesh file. So you have it here, mesh1, so that's the one I just created, my beam. I can activate the format, which is met format, and I just click OK. Okay, and you see that every time you create a new function here, then in the information you have the way it is actually displayed inside the command text file. So I'll show you at the end how to export the command text file and see the whole file. But for the moment, just know that you will have that like that, and it's important because you will, if you go on internet, you search for tutorials for Code Aster or something like that. Generally, they just give you these command files, so you can compare if you have the same commands than the file or not. So I read the mesh, and now it's okay. I have nothing more to do in this area here. Now what I have to do is to assign a finite element model. So let's go here and let's add a finite element model. So I'll just define everything, and this is a mechanical model. And here I have to choose the type of element that I'm using. So you see there are a lot of choices: 2D bar, 3D mesh, a lot of types of elements here, axis symmetric, cable, coq. So coq means actually shell in French. So it's not what you think. Yeah, they could have called it shell, but I don't know, they prefer to call it with the French name. And then plan, okay. And then here you have poutre. So poutre means beam in French. So that's what I'm gonna use for this 1D element. And you see you have different types. You have DE, DEM, DT. So how do I know what it means? Well, to know what it means, you have to go on the website of Code Aster, and then you will have the definition of what it means. So I'll show you right now. So there is a document which basically, so I'll resume you quickly. The modelization of this type of element, so it means straight beam of Larian. And if you have T, it means straight beam of Timoshenko, and this is CT means curved beam of Timoshenko. So basically it's different ways to calculate the beam elements. So the straight beam of Larian means that it has the Bernoulli assumptions, which assumes that the section remains right and perpendicular to average fiber. So this is the basic assumption we use in most structural calculations, so I'll just use that. Okay, now we're back, and let's just create this model. Let's just validate that. Okay, so we have defined the model. Now, there is an additional step that I have to do, which was not necessary in 3D element, is this one. I need to add this comment, affy chara element. which will be used to define a section of the beam. And here I have to choose the element I'm using. So I'm using the first one, poutre, which means beam in French. So again, you will learn a few words of French with me together. That's nice. Unfortunately, a lot of words in Code Aster are still in French, but you know, I cannot do anything about it. It was developed like that, so that's the way it is. Okay, so here you see that, for example, I have different choices of section. Circle, which in French is called cercle. Coude, which means that there is an angled type of section. General, rectangle. So those are very similar. So let's just use the most simple, the circle. And then I have to assign that to a group of elements. So click here. And here you see that I have the group of elements that I created previously in the meshing step when I was doing the meshing. So I told you that I needed that, and that's exactly for that, to be able to select it here. Also, a remark, this is important, is that you have to create first your model of finite element. If you do the element property first, then you will not be able to select the elements here. So you have to go in the same order than me. Now, Cara means characteristic, so it's basically characteristic of the section. So for the circle, you have to click here to see what are the two characteristics available. So you have R and you have EP. So what does it mean? Let's go quickly again on the website of Code Aster and the documentation to see what this actually means. So let's go on Google and search this Cara element Code Aster, or just this, and you will find basically a PDF with the information about these functions. So here I'm lucky because it's explained in English. I saw some others where it was explained in French. Okay, let's go down. And basically each type of elements will be explained here. So if I go down, to, so here I have the bar element, and here I have, okay, so this is the circle element here. When I choose section circle, I have two parameters, R and EP, and R is the external ray external of the tube, and EP is the thickness in the case of a hollow tube. So if I have a hollow tube, I have to input these EP parameters, otherwise I don't need that. Now for another right angled section, then I would have more parameters to enter, etc. So if you want to know the details, go and find this file. Okay, now we're back, and let's just assign those two. So R, and then I have to assign the value which is associated to R. So for this tutorial, I just use 100 millimeter, so around 10 centimeter for the external ray. So I think it's okay. External radius. So, and then let's add another one, which, well, I don't have to define that, but I want to try it. And this is the thickness of the tube. So if you have a tubular section here, so now I'm defining a tubular section with a 20 at the thickness, so 2 centimeter of thickness. Maybe it's a bit too big. Well, let's use 10. Anyway, okay, that's done. Click on OK. And now my element here is defined. Okay, my model is defined as well. Click here. Okay. So that's set for the model definition. Now the material. So we have to define a material first. So we have to give a software material, so we'll call it matter, and this will be linear isotropic material. So let's use the characteristic of one steel, for example, material. So I have to use 9 zeros, GPA 1, 2, 3, 4, 5, 6, 7, 8, 9. And the Poisson's ratio 0.3. Okay. For density, I don't need it. I won't have gravity in this analysis, but if I had gravity, I will need to enter that as well. Click on OK, and that's it. Okay. Now I have my material, and now I need to assign my material. So I assigned my material to my model, so I have to choose either one of those. Either I can assign it to the model or I can assign it to the mesh. Let's assign it to the model, and let's choose my material. So I just choose everywhere, and I choose the material that I just defined previously. Okay. Now I don't have functions and lists, so the next step will be boundary conditions. So let's assign a mechanical load. So it's called mechanical load, but actually it's used to define boundary conditions as well as loads. So let's define first the constraint load. So let's define a fixed condition, and here I have to use enforced DOF. Okay, and let's edit. Okay, and here I have to choose the group of node. That's where it's useful to define it beforehand. So choose the left node. So this is the node here, and here I could just select all degrees of freedom, the 6, and just put the displacement to 0. Or I can choose this liaison, which means link in French, encastré, which means fixed. So basically, again, two French words, but now we understand what it means. It means that you suppose the beam is fixed on this end. So it's basically fixed all the degrees of freedom. So let's choose that. Okay. Okay. So I have my first boundary condition fixed on this end. And now let's define load. So let's define load, and on this end here, and the load will be force nodal. So this is nodal, so I only see one part here, but it should be nodal, and that's what I'm searching for. Again, define a group of node on the right, and this is force applied in Z direction, so minus 100, and I have kilonewton, I think, so I have to use 5 zeros. Okay. Okay. And this is linear static analysis. So I have okay, so I apply the load, I fixed this end. Okay, so now I can compute my model. So let's not yet, not compute exactly. I still have to define the analysis. Sorry about that. So analysis, and here this is a static mechanical analysis, so I choose that. And here I have to define the material and the element property. So I have to assign both in this case because I have material and I have a section, so I need both. Model, load, and here let's just assign the loads. Okay, and I have two loads. So, well, basically I have a boundary condition and I have a fixed load. So let's assign both. And that's okay. And finally, let's define the output condition. So output results. So now I have to tell basically where the result will be saved. So I have to create a new file called beam2.resu like results.med, and you need to use the med extension, otherwise I think it will not be recognized when you try to open it with ParaView. And click here on format to tell it that this is the med extension. You have other extension as well, but this is this one we're using. And you have to assign some results as well. So we want to get linear static results, so we check that result linear static. Okay. And now basically everything is ready. And okay, I told you that I could generate the command file. So to do that, so you don't have to do that, but you know, if you want to see what it looks, you can export the command file like that. And now if I go into my, sorry about that. If I go into my files, I should be able to, to see it. So it's called beam2. I don't know if I was able to successfully. Okay, I didn't export it. Okay, I'll call it stage1.com. Save. Okay, now it's saved. Now if I go again, okay, I have a file called stage1.com. If I open that, now I have the command file. So you see, this is basically everything I define in Aster study can be resumed in one text file. So if you could just, you know, modify the text file with the right functions and just run everything again, so you wouldn't have to, you know, go over all the steps in the graphical interface. So for people who are really familiar with the name of the functions and what exactly they need, a small change here and they can run over and over the analysis, so that's pretty useful. But for those just starting like you, probably if you're watching this video, well, this is more complex probably. So let's go back to the model, and now my model is basically ready for computation. So let's see how to do that. So I have to switch to history view, and let's activate the stage and run. Okay, run that. And now I hope it will work. Great. Calculation is finished. I got the results. Perfect. In case you have an error and it's red or orange, then you have to go and look at the message and what is written, and maybe you forgot to define something, so you have to come back and define the right and search for the function that was not defined correctly, and then correct that. Okay, now it's defined, so it's okay. So now I go in data file, click here, sorry, and then you have open in ParaView. So you click here, and then it will change and open ParaView, so you're able to look at the results. Okay, now I have my beam, but I don't see anything. So in order to visualize by colors, I have to switch to another type of visualization, and now you see that I can see the colors here. So red means that there is a deformation, and white is means that, so blue means 0, and basically, so you can create custom filters also to visualize better your results. And here you have some options here. So if you want to see the displacement, you have to, I think, generate vectors. Okay, apply. And then let me check that. So mesh. Okay, outline. Okay, wrestling displacement. Okay, so here in this displacement basically, and here you have displacement vector magnitude. So now you can see the magnitude of the displacements. So in blue it's almost 0. You can say it's 0. In red it's also very small. And now you can change for different. So now displacement I'm observing is in DZ direction, so I can choose DZ, and you have actually, well, you don't see well, but you have the deformation of the beam here. Wireframe. Okay, that's all for this tutorial. So I'll do a more complete tutorial in the future about visualization of the results in ParaView. Thank you for watching this video. I hope you learned a lot from this, and that you are now able to simulate beams, and in the future I'll also create more complex models with several beams and try to link them together. So if you want to see something in the future, just write a comment either on the video or in the blog in the comments, and I'll try to do this kind of model for the next tutorial. Thank you very much for watching again.